So our next speaker is Andrea Bajcsy. Andrea is an assistant professor in the Robotics Institute at Carnegie Mellon University, where she leads the Interactive and Trustworthy Robotics Lab. She broadly works at the intersection of robotics, machine learning, control theory, and human-AI interaction. She's the recipient of several awards, including the NSF Career Award, Google Research Scholar Award, and Rising Stars and ECS Award. Please join me in welcoming Andrea.
Thank you, everyone. Is the audio working? Can everyone hear me? OK, fantastic. So it's my great pleasure to be here to talk to all of you. As you can tell from my bio, I'm actually a roboticist by training, so I'm a little bit of an outlier when it comes to this community, but I'm really excited to learn from you, and hopefully maybe I can also teach you a little bit about where I'm at as well. And the way I'm going to start is in a way that we all predict, which is that there's no need to convince you all that AI agents are the rage. I'm sure many of you have seen the Agentic Commerce that ChatGPT recently, or OpenAI recently released. But of course, we've seen a lot of work over the past few days on web agents and coding agents. Now, for me as a roboticist, what I think is so interesting, though, is that increasingly these same kinds of agentic AI paradigms are starting to be pushed more and more into the physical world, specifically for robots. So for example, on the left-hand side here, this is not my own work, this is work from NVIDIA, where they get essentially a large language model to analyze the scene that an autonomous car might see. It takes as input some requests from the driver, and this LLM agent acts like a driver assistance agent to kind of tell you what you should do next, like immediately slow down here, because in Switzerland, drivers must yield to emergency vehicles. And so it can kind of give you this advice for how to drive more safely in different environments. Maybe some of you have also been following the results from Gemini. So Google has a Gemini robotics team where they're integrating a lot of these Gemini models within the overall robotics autonomy pipeline, and you'll see demos like this oftentimes pop up on Twitter. The other thing I think is quite interesting, by the way, is that if you actually stare at a lot of the hottest models in robotics right now, they're starting to look more like agentic LLMs. So on the left-hand side is a very standard LLM model that you might see. So it takes as input some task requests from a user, like what items should I buy for dinner. Maybe you get some HTML of the current website environment. You tokenize it. You predict some next action. And if you stare at the hottest models, which are vision language action models, let me actually ask the audience, how many of you have heard of a vision language action model? Raise your hand. Right, OK, so great. You already know that they end up looking really similar. Right, you're passing in text and images, and you're predicting some kind of actions. In this case, for robots, it's typically going to be some end effector, like the gripper of the robot, like displacement, maybe a gripping action, things like this. OK, so because we're starting to see these similarities pop up, and because we're starting to see a lot of these kind of this interest in generalist agents, this of course has gotten a lot of people worried that these increased capabilities and deployment are going to actually maybe lead to some unsafe outcomes. And here are just a few samples across governments, academics, and industrial partners who are all quite worried about this problem. Now, when we talk about AI safety, there are a lot of facets to it. We've already seen many of these over the course of the past few days. And in today's talk, I want to zoom in on just one. I want to focus in on deployment time guardrails. So you deploy your model, it's out in the world, what do you do to make sure it does the right thing? And very, very broadly, you can categorize most guardrails as either input or output guardrails. Right? So an input guardrail is like monitoring what's in the environment. It's checking if there's, let's say, malicious edits to the scene and maybe rejecting these. And then there's output guardrails, which are checking what is the model actually generating, and typically doing some kind of operation on that. And I specifically want to focus in here where when we talk about output guardrails, the predominant paradigm you'll see, at least I've seen when I look at the literature, is as soon as the guardrail fires and it says, this generation is bad, I suggest you eat a few rocks. I'm sure many of you have seen this example that came up from Gemini. What happens is typically after you do detection, the model ends up doing refusal. So the model says something like, sorry, I can't respond. This is the way in which the system reacts to the detection of an unsafe generation. OK, so this is kind of where we're at with non-agentic settings typically. Now, what I want to ask is what makes agentic AI guardrails somehow different, maybe even harder than non-agentic guardrails? And there's a few facets of this I want to highlight. The first is that when you have an agent that's generating actions, this is a policy, right? You have to somehow translate these actions into outcomes for proper evaluation. So simply just looking at what the model is generating is not informative enough. What you have to do is you actually have to take that action. You have to somehow pass it through a controller. I'm calling it controller because I'm a roboticist. This could be, for example, API calls or other things like this. This gets translated into some real outcome in the real world. And I want to be clear, this is not just the web agent like the web browser. This is, for example, the actual state of your bank account. This is how you feel about the agent, your internal state, for example, as a user. The true state of the world, which is far too complex that we could ever possibly have a handle on, but that's actually what happens. Okay, and then what you're going to do is the agent is going to get observations about the true state of the world, for example, in this case, text, and then it's going to make another decision. So this is a really, really complicated process, right? But there's another problem here, too, is if you stare at this model that's going on under the hood, the model itself has to actually do this very hard process of inferring the state of the world given the lossy observations. Right? Does the model understand the state of the world given just O, where O is typically text? It can also be images, of course, right? Is this a sufficient representation of what it needs about the state of the world? And finally, I just want to ground this example in robotics. In robotics, this is particularly salient because it's super, super hard to know the true state of the world. It's super hard to know, for example, in a deformable object, what exactly should you be representing that deformable object as? We'll do an exercise later on this. And the kinds of observations you're getting are things like text, RGB, touch, so on and so forth. And the final thing which is most relevant for guardrails is that for many contexts, actually refusing to act in and of itself is unsafe. Right? So if my guardrail here for this VLA model fires and says, oh, the robot's going to make an unsafe decision, I am going to not execute this action. Okay, I have to do my obligatory robot fail video. Here's a little robot fail video. Sometimes refusing to act in and of itself is unsafe. Okay, so the core argument in my talk today is going to be that if we want to talk systematically about agentic guardrails, instead of writing down heuristics or writing down these proxies on like the output of the robot or the agent's text generation, for instance, what we should be doing is we should be actually automatically computing these guardrails. We should be computing these guardrails through, and what I'm going to argue is a special type of sequential decision-making problem. Specifically, what we're going to do is we're going to use ideas, old ideas from safety-critical control theory. But what we're going to do is we're going to do all these computations within the AI model's latent representation of the world. That's the best it could do autonomously, essentially. And the outcome, the thing we're going to build up to in this talk, is we're going to get an agentic guardrail that first, it's going to do the monitoring. It's going to tell us when the AI system's outputs, actions, are going to be dangerous in real time. But we're also going to get a feedback policy that's going to correct those risky actions to safe ones. Okay. And this is all going to be done in a model-agnostic manner. So the same guardrail can apply for any AI agent. And this is kind of how we're going to be building up from refusal to recovery, hence the name of the talk. All right, and so the key tooling we're going to be using here, we're going to be uniting these two paradigms, robust control, that's the lens through which I've been trained as a scientist, so that's kind of where I'm coming from. But we're going to be modernizing all of this into the generative AI paradigm. And so this is the roadmap for today's talk. The first thing on my agenda is I need to teach you some safe control. And I know it's going to be a little stressful. It's almost 4 p.m. I hope you all had coffee because we're going to look at a little bit of math, but I promise it's going to be OK. So let's first talk about the common ground here. What is a control-theoretic guardrail? And the idea from control theory we're going to be pulling on is this idea of a safety filter. This is what we call it in my community. Okay, a safety filter wraps around any decision-making system. And what it's going to do is it's going to minimally modify the output of that decision-making model so that the current actions do not result in future failures. Now, the trick is always computing it. But there are a few ingredients we need to do this computation. All right, so the first ingredient we need to compute a safety filter is going to be a representation of state. So for example, in this running scenario here of this little ground robot that's moving around the environment, the state space is actually quite simple to write down. For example, the XY position of the agent, its velocity, its heading. The next thing you need to do is you need to predict outcomes. You need to know what's going to happen next. And this is what we need. World models, dynamics, transition models, these are all the same kind of concept to essentially convert an action, this is denoted here by U, and the current state x into the next state. It can be a simulator, it can be a world model, whatever you want. Oftentimes in robust control, when we're talking about safety, we want to kind of consider robustly uncertainty. So this is what we typically call an opponent model. It's a disturbance, hence it's denoted by D. It can model a variety of things. Hard to model aspects of the world. It can be an explicit adversary, an explicit, let's say, attacker. And then last but not least, we need to actually specify what safety means. You need to tell me what failure looks like. And in this simple example here, it's quite straightforward. If I know exactly where all the obstacles are in the world, my failure set is my robot enters into one of those obstacles. It collides. OK, with these ingredients, we're going to actually compute this safety filter together now. So here's my safety specification. It's a failure set. It's a subset of the state space. I'm showing you a top-down slice of the safety, the failure set here in gray. This is just the obstacles. And what we're going to do is we're going to use a particular control-theoretic tool. It's called Hamilton-Jacobi reachability. If you want to do more reading, here's some references. And what we're going to do is we're going to encode the safety, the failure set as the sub-zero level set of this function. Think of it like a sign distance function. It tells you how close are you to failure. And now the optimization task we have is to ask ourselves, from any initial condition, x, what's the closest my system could ever get to failure despite its best effort to prevent failure? And of course, here there's this disturbance that's perturbing you. And so what this looks like formally is a safety critical dynamic game. It's OK if this equation doesn't make much sense. Here's the intuition for it. Intuitively, this value function, the optimal value of this game, remembers the closest your system ever got to failure under the best strategy that your AI, your robot had, and under the worst response of the opponent. There are many solvers these days for actually computing the solution to the safety critical game. There's exact solvers in very low dimensional states. For high dimensional states, you can use adversarial RL, self-supervised learning. And here's one such solver being run in real time here. You see the value function growing and changing. It's so beautiful. Let's watch it twice. OK, I love seeing that. Now, what do we get to extract from this? We get to extract two very important quantities. The first is a safety policy. So what I can do is I can tell you not only what the best strategy is for you to keep yourself safe, but I can also tell you this safe set, so all of the initial conditions from which there exists something you can do to stay safe. And specifically, it's encoded as the super zero level set of that value function. It's a very special structure of our optimization problem that we had that gives us this property. And so for instance, if I queried my safety policy for all these initial conditions, let's say my robot is facing upwards, so I'm looking at this slice with the heading pointing upwards, the optimal policy or the safety policy is very intuitive. It's just like steer away from failure, right? Steer away from those obstacles. And the way we typically apply the safety filter is in a least restrictive sense. So as long as you're inside of that safe set, well inside of that safe set, you can do whatever you want. Run whatever policy you care about. As soon as you get to the boundary is the last moment, the boundary of this red set here. The boundary is the last moment at which there exists something you can do to prevent failure. And so once you get to the boundary, you have to apply pi shield, the optimal safety policy. Because after this, you're doomed. There are many ways of doing safety filtering. This is just one that I'm going to use throughout the talk. Now, here's an example of this working in real time. So here, the failure set, the obstacles, are actually being inferred in real time. The robot's using its sensor measurements to figure out where the obstacles are. And we're running a vision-based policy that's taking in those RGB images you see here on the lower right-hand side. And the RGB-based policy is a little unreliable. It's trying to take these shortcuts through the obstacle. And so the safety filter, it takes over control at the last moment to prevent the robot from hitting these obstacles. That's how it kind of interplays. And then whenever the robot is well within the safe set, it lets the base policy do its exploration again. OK, these are the foundations. Let's now actually talk about generalizing this to much, much more interesting, much more complicated settings than just a little ground robot that's navigating. And the key motivation for this line of work was to say, well, if I'm going to deploy a generalist agent in the complexity of the world, the space of unsafe outcomes are super complex, right? It's like tearing, it's breaking, it's spilling, it's all of these kinds of problems I'm showing you here and more. And so let's just stare at one of these and ask ourselves, why is it so hard to get a guardrail for this? What's holding us back? And the specific example here is a little robot is going to pick up this bag of Skittles, and all of the Skittles spill everywhere. Okay, this is an undesirable outcome. I really like Skittles. Now, let's go back to our cookbook, and let's ask ourselves, OK, I need a state space. Well, what's the state space of this problem? And usually, if this was a smaller, kind of room, I would ask you, I would pick on you to ask, to tell me what state space do you think. But do that exercise in your head. You have to write down the state. Is it going to be the position of all the Skittles? Does the color matter? What about the deformable bag? You have to also forward simulate the interaction with the bag. That's the dynamics function. Who's going to give you a high-fidelity simulator of this? There exists no high-fidelity simulator of this kind of Skittles bag right now. My student tried very hard to find one. There is not one. And even if you had all that, how do you specify the failure set, right? Most of the time, those Skittles are inside the bag. You can't even see them. And so even though, it's very hard, right? But even though we don't know how to write down the state space or maybe the failure set by hand, we can leverage one nice thing, and we're going to make an assumption. We're going to say that the failure states are observable from high-dimensional observations. If I show you an image with the Skittles on the table, you can tell me, yep, you've definitely failed. You've spilled. The problem is that once you've seen those Skittles, it's too late. It's too late. You've already failed. So the robot needs to predict if it's going to see this in the near future to prevent it. And so here's where we said, well, let's just do all of that safety-critical control computation we had before. But let's now do it inside of the latent state representations of generative world models, which are going to compress high-dimensional observations into some low-dimensional state. And we can now run all of those nice control-theoretic tools to compute a safety filter. And so here we're comparing before and after these two equations. I'm going to show you a little concretely why they're so different. This is the universe we were in before, where I had to write down by hand every aspect of the state. I had to have a really nice simulator like Mujoko, and failure was this really hard function to write down. Now my state is just an embedding of some sequence of images, and failure now is going to be some classifier that lives on the embedding space, and it's going to say, does this look like failure or not? But I don't have to decode, right? I'm just looking at the latent state directly, and I'm going to do forward simulation by using this world model. So let's start here. I know many folks have talked about world models today, so I'm going to go through that quite quickly, but I'm going to show you the specific architectures we use throughout. So for world model training, what we're going to do is we're going to collect a diverse set of observations. Here, this is the robot's proprioceptive state, a wrist camera, and a third-person RGB camera. We staple all that data together, and we have the corresponding robot actions that it took. So you have this big data set. And your world model will encode these observations into some lower dimensional latent state. Like, for example, here's Z is like, 512 dimensional or something. And then what you're going to do is you're going to learn a latent dynamics model, a transition model, on this latent state. Okay, you can train it via many ways. There are many, many models you can use. The specific ones you're going to see in the rest of my results are these two. So this recurrent state space model, this is Dreamer v3, and a recent transformer-based model called Dino World model. Okay, so we have our state representation that's inferred from data. We have a dynamics model. What about failure? Well, I told you before we're going to make the assumption that we can observe failure. And so what we can do is we can say, let's train that classifier by getting labels from our world model data set of what looks like failure, what looks like not a failure. Train that classifier. And essentially, the loss function here is just penalizing latent states that are truly in failure from being classified as positive and vice versa. And this gets us that safety specification I showed you before, where essentially if L, that function L returns 0 or less than 0, this means that you're in failure. If it's positive, you're good. So now it's time to do safety analysis to compute our guardrail. Here's what we're going to do. Here's the optimization problem. What is this optimization problem intuitively doing? Here's your latent representation, your world model's latent state. There exists some subset of these states that L function is classifying as unsafe. So for instance, if I took a latent state in here and I decoded it, I would see Skittles. These are real decodings, by the way. Okay, now my optimization is going to take an initial observation. It's going to embed it into the latent state, and it's going to now do forward simulation all in the latent state space. And the optimization intuitively here, because we have this max min over time, it's saying, given the robot's best effort to avoid failure, because remember, L returns negative if you're in failure, and you're doing max over the policy. So what you're doing is you're saying, OK, the robot's trying its hardest to avoid failure, and it's remembering this min over time, the closest it's ever going to get to failure. But it's going to do this all in the latent space. And so what you're going to do is if you ran this computation, this is the Bellman-style backup. Again, it's not too important for you to understand the details, but if you're familiar with MDPs or POMDPs, this is kind of an equivalent version of a Bellman-like operator, but for the safety-critical control problem. If you were to run, let's say, RL with this kind of safety-critical Bellman operator, you would uncover this latent unsafe set. And it's very beautiful. I'll show you why. Okay, automatically by just churning through the computation, I discover the following initial conditions from which I'm doomed. An initial condition like this. Imagine my robot's teleported into a situation where the bag is already lifted up high. There is nothing the robot can do to prevent those Skittles from spilling out. It's just physics from that point on. And so the robot is doomed. It should never get into this situation because it cannot recover from it. But we automatically discover these initial conditions just through the computation, which would be very hard to write down by hand through a series of rules. OK, so as I said, the computation gives us two things. The value function, the optimal value function, is going to be our safety monitor. The sign of the value function is telling us, am I in the unsafe set or not? And then the value function comes with an optimal policy, and that optimal policy is going to try its hardest to stay away from failure. So that's going to let us recover. It's going to let us steer away from failure. And so at deployment time, if you look back here, the way you're going to run this in the loop is you're going to take the robot's observations, you're going to encode them. The robot's going to be running whatever task policy it wants up until it gets close to the boundary, just like we saw before when we all learned about control theory in like 2 minutes. At some point when you get close to the boundary, you realize, I'm almost at the point of no return. Right? Here, if I keep going, I'm doomed. And so here's when your safety policy takes over, and it corrects you. I'm going to show you some actual recovery behaviors in 1 second. So in hardware, we're all familiar now with this Skittles example. Here are the real observations the robot gets to see, the third-person camera, the wrist camera. In all these demos, you're going to see the task policy is going to be actually my student teleoperating the robot. We specifically chose this because that's one of the hardest, policies to ever have. You have no idea what a person's going to do. And so it really showcases the policy-agnostic nature of the guardrail. If my student just naively teleoperates, you see that failure happen really easily. Everything spills. OK, so now we say, let's go train our world model. Just for reference here, the world model is trained on 1,300 trajectories. Most of them are random. That's part of the beauty of a world model is you don't need optimal data. Any data is sufficient. You just want coverage. It's a system identification problem, right? So you want to see lots of diversity. We do that safety computation offline before the robot is deployed to discover the unsafe set. And then here's what happens at deployment time. So the way to understand these visuals is the top row is all just the third-person perspective of what's happening. By the way, if you're ever in Pittsburgh, come to my lab. This is a really fun demo to do. On the bottom, you're going to see what the robot sees in real time. So we're running the safety filter at 15 hertz. Okay? And whenever you see a green border on the bottom videos, it means the robot is in control. It means the robot is querying the safety policy to protect the base teleoperator. OK, so on the left-hand side, my student is going to grab the top of the open Skittles bag, and you see there's no green border. He is fully in control because there's no reason to be worried. There's no way that an unsafe thing can happen. In the middle, he's going to grab the bottom of the Skittles, and he's going to start to shake. Now, what does the teleoperator, how are they getting corrected whenever the green boundary shows up? The robot's slowing him down. The optimal recovery policy is to slow down, because if you shake the bag really fast, the Skittles come out. But you don't have to stop shaking the Skittles, just don't shake them that fast. OK, and then on the right-hand side, when he's going to grab the bottom of the Skittles and pull up super hard, the controller blocks his command entirely. So you can see him, he's going to grab, he's going to pull up, and he's pulling up, but he's being blocked entirely, right? Because, OK, I'm sure that you're going to spill those Skittles if you pull up. OK, and this is all from the same policy. So here's a closer look. This is an uncut version of what you just saw. On the lower right-hand side, you see that safety value function running in real time. It's predicting the safety value of the next state, assuming you just kept doing what the teleoperator wanted to do. OK, that dashed line is that important 0 level set boundary. So as you start doing riskier things, your value function's getting worried. It's like, ooh, you're getting close to failure. And then as he grabs the bottom of the Skittles bags and pulls up super, super hard, the value function dips a lot, and it says, if you keep doing this, you are definitely doomed. We also tried to perturb this, so we only trained on Skittles, but I have a new appreciation of all the different flavors of Skittles out there. So we tried sour Skittles and wild berry, and the same safety policy can shield, it's quite robust to all these different visual perturbations of color and like background, just zero shot. I do want to show you some failures. That's one of the nice things about doing robotics. I think we should all share what doesn't work, because a lot of things don't work. Here's one problem, observability. I take the Skittles bag and I rotate it. I rotate it so the opening is not visible by both the wrist or the third-person camera. The filter doesn't activate. Not surprising. On the right-hand side, I changed the dynamics. Okay, so I put peanut M&Ms instead of Skittles. I have a greater appreciation for the difference between peanut M&Ms and Skittles. Peanut M&Ms have like a much more papery bag. Skittles are much more plasticky. Okay, it doesn't generalize to this. You saw the small data regime we have, but it's important to just be aware. There's another challenge here, though, too. And I like to look at this example of Jenga, because if you really look at this example, you'll notice that you really can't safeguard what you can't predict. And I'm sure that this combinatorial nature of like all the possible ways in which the Jenga tower can fall is something none of us have ever gotten coverage for. We haven't seen every possible way a Jenga tower can collapse. And in practice, what this really means is that when you use these world models that have some finite coverage, they're going to end up being unreliable. In fact, they usually end up being optimistic. So the bottom videos are all imaginations. And the bottom videos you'll see end up having optimistic imaginations of the outcomes whenever you start taking actions that you've never seen the outcomes for, like the blocks not falling down. And so this is where we started to think, okay, well, what does it even mean now to talk about safety when you have all these like learned representations, learned world models, and all this kind of stuff? And if we go back to our safety problem, what we said was it actually looks something like this. The coverage of your world model actually looks like this. You only have a portion of the failure states covered in your data set. Like I've seen, maybe the blocks fall to the left. But whenever I start using the model and I start predicting the outcomes of certain actions, the world model has never seen certain transitions, and so it can't reliably tell you what's going to happen next, whether or not it's going to be safe or unsafe. And so the idea here instead was to say, well, maybe the notion of safety should not just be known failures. It should actually also be a notion of uncertainty. So for example, whenever my world model itself is super, super uncertain about the next outcome, this should be a proxy for me to probably not take that action. And so what we did here was we said, let's use that epistemic uncertainty of the world model as a proxy for specifying unseen failures. You see them here in purple. I agree, it's more conservative than you would want, right? It's a superset. But what it lets you do is it lets you cover these outcomes that you've never seen before, these uncertain failure situations. And essentially what you do is when you do optimization with this safety specification, that's the combination of out-of-distribution states and known failure states, you get a safety guardrail that keeps you in distribution and away from known failures simultaneously. So here's an example side by side. On the left is a robot that's running the same safety filter we just saw before without any of the uncertainty quantification. And here, when the teleoperator tries to pull the block, the safety filter is unreliable. It's very optimistic about what's going to happen next and lets the teleoperator do this unsafe behavior. But when you start injecting this uncertainty-aware safety specification, you see this really nice recovery behavior here in the center where the robot resists. It's pushing the block back in whenever the teleoperator is trying to take this risky action. The final thing I want to talk about, which is actually connected to some of the things we've seen today, is that what safe behavior even means, what a safe recovery behavior is super context dependent. For example, if you're picking up a bag of Doritos, right, a bag of chips, it's okay for me to crush the interior of that bag if I'm trying to make a crunchy topping. But if I want to use this as an actual snack, I don't want to be crushing the interior. And And so this is where we started turning actually more and more to these LLMs and VLMs, these foundation models, for how can we use the knowledge within these models to somehow enable this context-dependent failure recovery behavior. And so this is the final work I'll touch on. And the setting is very similar. We have a manipulator again. Now the base policy that we're going to be shielding, that we're going to be safeguarding, it's a generative policy. It's specifically here, it's a diffusion model that generates actions. So given some observation here, the observation again is the robot state plus the wrist camera and the third-person camera. It generates an action sequence. And it's trained on a mixture of data. The robot knows many ways of interacting with this object. So for example, if you sampled from this model, you'd see these different action trajectory clusters essentially emerge. The challenge, though, is that not all sampled actions lead to the same task performance. For instance, if I get lucky and I sample this action, which the task here is to serve a cup of water to the guest, this looks pretty appropriate. I got pretty lucky. Life is pretty good. But I could also sample this action where the robot puts its fingers in my cup. And that's not very good if I'm trying to serve someone some water or some juice. And then there's also samples I can get where if I execute them, they just result in bad outcomes, like the cup toppling over. Now, what I like about this example is that the base policy isn't useless. It does actually contain the right behavior modes within its distribution, oftentimes. But the problem is that we can't just blindly execute actions. We have to actually verify if the samples you're getting, the sampled actions, are actually leading to good outcomes, good here being context dependent. And so the way we thought about this, we kind of formulated this idea of policy steering as a model predictive control problem. You can also think of this, if you want to use the hottest terms, you can think of this as kind of like embodied, like test time compute. And the problem looks something like this. So you get to optimize over which sample you get to actually run on the robot. These are the different samples here. And the first task you have to face is you have to translate these actions into outcomes. Right, so you actually need to think about some distribution of future observations you're going to get, given the current observation and the current action sequence you're considering. And then you need to verify. You need to check, is this the right thing? And the way that we're going to inject this notion of context is through natural language here. So L here is the task context described in language, in text. Of course, the big trick, of course, is always how to actually solve this tractably. And here's where we're going to go back to a prior idea we saw before. Let's do the outcome prediction, again, in the latent representation of a generative world model. And what we're going to do is we're going to actually align a vision language model to directly reason about these latent states for evaluation. So let me show you how this works. We follow the same procedure. We take the current observations the robot can get. We encode them into the latent state representation, ZT. For every action sequence that I'm considering, I'm going to forward simulate the outcomes in my world model. So I'm going to get a latent state trajectory, ZT to T plus T, big T. And if I decoded each of these, here's what I'm seeing, actually. These are real decodings. You're seeing these different outcomes. You're seeing the robot grab the handle. You're seeing it grab by the lip. You're seeing the cup topple. But we're not going to do the reasoning in the decodings. We're going to do the reasoning directly in the latent state. Because that's already kind of we're making this assumption that's already a sufficient representation of the world. That's our state. There's no need to go back into observations again. Z is already everything I need to know. And so what I'm going to do is I'm going to pass these Z's into a vision language model that has been aligned to specifically actually translate these latent state trajectories into textual narrations. So the VLM, in this case, Llama 3.2, 11B Vision Instruct, its task, it's fine-tuned via a visual Q&A task to describe in text what's happening in these latent states. And what this really lets us do is it lets us unlock a VLM off the shelf as a really strong open world verifier. Because we've essentially taken these embodied outcomes and put them in the representation that the VLM is really good about reasoning at. It's text. So for instance, here's a real prompt. The robot wants to grab the cup from the table, and we ask the latent aligned VLM, okay, can you describe each of these latent trajectories? And we're going to get these behavior narrations. The robot attempts to grab the cup by the handle, seizes the cup through the interior, fails to achieve a secure grasp. Then we ask the VLM again, okay, here's the task context, serve the cup of water to the guest. Which of these is the best? And the VLM says, well, I think mode 1 is actually the best because it's the most suitable way to serve the cup to a guest without spilling or contaminating the drinks. And so if you think about it, the VLM itself is actually doing this argmax in the optimization too. So here's some pretty videos, because that's what we do as roboticists. We generate really pretty videos. So here on the left-hand side, you see our policy steering method selecting the correct mode here. But on the right-hand side, all we do is change the task description. So we change the task to be, oh, the handle is covered in oil, and automatically a different mode is selected. You can do this for other objects too. So you can say, avoid crushing the contents inside versus maximize stability without dropping the bag, and it automatically chooses different behavior modes, just conditioned on different task prompts. And you can also do this for longer horizon tasks where you call this steering framework multiple times in the loop. So at the very beginning of the interaction, maybe you have the following setting. So you want to place the fork in the bowl while maintaining sanitation. You have multiple modes of how you grab the fork. You narrate all of these outcomes. You ask the VLM again, which of these seem the best? The VLM picks grabbing by the handle. Then what you do is you query the model again. You get your behavior narrations. Oh, there's certain outcomes like dropping the fork outside the bowl, or you're failing to even place it into the bowl. And so the VLM again selects the correct behavior mode and kind of carefully drops it in by the tongs. We have many, many results in the paper if you want to take a look. I just want to quickly highlight a few here that might be of your interest. One thing we did was we took the base llama model and we gave it the same exact input that our overall pipeline for Warren here gets to see. And the input is an action trajectory and also the current observation. And we fine-tuned the llama model to do narration directly from just the current observation and the action trajectory. So implicitly, the model has to learn to do prediction of outcomes. And we found that, at least in our data regime, which is very small, it's really hard to get the model end-to-end to understand how to narrate these outcomes accurately enough for the overall success rate to be high of the overall system. And if you take a closer look, you see that a lot of the failure modes come from kind of the granularity with which the VLM can describe the outcomes. So here are the cup task and the bag tasks. These are true observations of what would actually happen if the robot executed its actions. So these are some of the narrations that we get with our method that takes the latent state, the latent world model state, and translates them into narrations, versus the end-to-end VLM model that directly takes the observations, the current observation, the actions, has to predict these images implicitly and then narrate. And that baseline really, it struggles to capture the accurate motion details and doesn't provide useful signal for guidance. And there's many more results in the paper too. For example, we also tried to give privileged observations to GPT-4o. It also doesn't do very good. Part of this might be related to some reasons that Jonathan pointed out yesterday, which was, there's like this too big of a domain gap. But this is kind of empirically what we find in our setting, but doing everything in the latent representation seems to really, really help. All right, with this, I'm gonna pause. I wanna just do some quick takeaways. So the first is, instead of hand designing guardrails or writing down a big list of rules, what I'd like to propose is that we actually compute them. We compute agentic guardrails by solving a special type of optimization problem, which is gonna really tightly co-optimize a classifier, the value function, that tells us are we doomed or not, and a recovery policy, PyShield, which tells us what to do instead. I think it's also really powerful to think about computing these guardrails within the agent's representation of the world that's built directly from its observations, if you want to have a really, really autonomous guardrail. And when we think about safety for these kind of frontier models, for these generalist agents that are trained on lots and lots of data, it's useful to think about safety not only from like actual physical failure states, but also from like a distributional perspective. Like, am I entering into unknown situations I don't know how to handle? And last but not least, safety is a very context-dependent concept. And here where we found, this is where foundation models can be really helpful for bringing in certain notions of context or common sense that would otherwise be very hard to write down by hand. I want to say thank you to a lot of the students who contributed to these lines of works and my sponsors. And with this, I'm happy to take any questions. And I want to quickly put a shout out. Coming soon, we've been trying to actually take some of these control-theoretic tools and start making them work in these more traditional agentic AI settings like Web Arena. And we're going to hopefully release some results on that soon. So please stay tuned. Thank you very much.
Thank you, Andrea, for the great talk. Do we have any questions? Please come up to the mic. Oh, great. Thank you, Chris.
Great. Great. Thanks for the talk. Very, very interesting. I know it's kind of big tech, but have you considered entering some kind of competitive Jenga competition and becoming the superhuman Jenga person?
I don't know what Jenga benchmark. Do you know of like a Jenga competition?
I just did some Googling. It seems like they do have competitions. I don't know if there's one key competition, but it seems like it could be cool, especially if you had like a KUKA that could do it super fast.
Yeah, I like that idea. I can pitch it to my student. I have not considered it though myself.
Cool.
Hi, this might be maybe a big question, but obviously when people talk about like AI safety, they don't just talk about like physical safety. And I'm curious what sort of your thoughts are on whether these generalize to those kinds of problems, whether those kind of problems are similar to the kind of physical safety problems.
Yeah, maybe let me take a stab at your question and tell me if you're looking for a different angle on the problem. But I think for me, the main differentiation comes down to like what you're trying to model. So for example, a lot of like AI safety, let's talk about like the alignment community, right? They care a lot about, is the system doing what I want it to do? And this ends up looking like a reward modeling problem to me because a lot of the phenomenon they oftentimes care about are easy to undo situations. When I talk about safety, I typically talk about it as constraint satisfaction. And the reason certain things should be modeled as constraints is because they're really hard to undo. It's very hard to undo breaking something or leaking your private information on the internet. And so from a modeling perspective, I think anything that's really hard to undo should be in the constraint and should be optimized maybe this way. Anything that is a softer notion of safety, like alignment, like are you doing what I want? Are you aligning with what I care about? Perhaps could be better modeled through more of these like reward learning paradigms.
Thank you very much. Very interesting talk. So I was wondering, just trying to understand the trajectory that you went from the embedding space and then moving towards more context-dependent representations and exploiting this external knowledge to see from the LLMs to see the failure modes. I was wondering how you deal with this trade-off between this richness of the representation and the interpretability of the failure. So to explain that, what I mean is like from the first case that you really have some notion of failure in your own environment. And then as you go, for example, you can have this natural language modality to explain the failure. You can even have the world model with diffusion models that actually models every pixel in your new environment that can be even more richer representation than like text. Then you have this issue of now how I'm interpreting the failure case, because why this is a failure might be missed in this case, right?
Can you refine what aspect of this paradigm is related to your question?
So basically, the richness of the representation, as you go forward, you go to more richer and richer representations of the failure case, and your model recognizes this is a failure. It can be explained in the language model. It could be labeled with, okay, the cup is falling down, or the water is pouring on the ground. So you can have like really a specific concept of failure, right? You can learn those and have an embedding representation of those. But you can have like a natural language explanation of this is a failure. You can have a like kind of diffusion model representation that's saying, okay, this is the world that I predict, and this is a failure. We will have richer and richer representations depending on the modality of failure representation that you're using. But then if you get to the richer models and go far away from this specifically like symbolic, like 5 cases of failure, then you have the issue of interpretability of, okay, your model says this is failure, but you cannot recognize why, because you rely on some raw natural language or visual modality now that says, okay, this is a failure.
I see. Maybe we can talk more offline as well, but let me say one answer to an interpretation of your question,
Yeah.
which is, and in my answer, I want to disentangle the way in which an agent builds an embodied representation of the world versus the way that it translates that representation into, like, for a verifier or for a classifier or for some kind of evaluation.
That's right.
And so, for instance, we have some recent work, we haven't put it on arXiv yet, but we have some recent work that actually RGB-only world models, they don't learn sufficient representations for certain classes of safety-critical problems. Like let's say you're cooking and you want to impose a temperature-based constraint. Okay, the latent state just built from RGB is not predictive enough, no matter how you decode it, to understand temperature. And it's because RGB is just not sufficient enough for you to infer those variables, right? But if you combine, let's say, infrared with RGB, now the latent state is enough for you to decode it however you want into whatever classifier, whatever verifier you care about. And so that's, I think, one.
Yeah, this is even more richer than what I mentioned.
I see.
That's right. We have like natural language, we have vision, you can have other dimensions that actually capture more than what we see.
Yeah.
But then if we just rely on this sensory information and detecting failure, then we cannot explain what was the reason of it.
Yeah, I mean, I don't even know what these representations mean right now. I mean, part of why I think decoding into the text with the last work that I showed you is kind of appealing is because it tries to give you some of that intuition, like what is the latent state capturing, and you can describe it. But I actually don't have a very, I have more questions than answers for your question about interpreting the structure of a latent space that's learned from either a single modality or multiple modalities. I think it's a very exciting research problem.
Yes, certainly. Thank you so much.
All right, please thank Andrea again.